Hi, everyone. So welcome to the seminars and the first one. Hi, everyone online, and thanks for being there. The first talk and only talk of today will be given by Michele Redi here from NFM Florence, and he will tell us about dark matter from dark gauge theories. Please.
Okay, so thank you very much, Filippo. It's really exciting to see people in presence here in Florence. We spent a long time in this building where there was nobody, and it was rather depressing, and now seeing so many people is really exciting. So I look forward to this workshop for the next 6 weeks. So I should mention that the last talk that I gave before pandemic, it was with Filippo that invited me. So I hope that everything goes fine. In Daisy, you remember? So what I want to tell you about today is work that we did with our group here in Florence, Andrea Tesi, Raghu Garani, on dark gauge theories in the context of dark matter over the past year. So let me start with some motivation. So the motivation is really from the standard model. It has to do with dark matter stability. So you all know that dark matter is stable, is cosmologically stable. In the standard model, there is another particle, which is the proton, which is whose lifetime is very long. And in the standard model, there is a very good explanation for this fact, which is the fact that standard model Lagrangian conserves accidentally baryon number. And so this guarantees in the standard model that the proton is stable up to dimension 6 operators, and so it gives you automatically cosmological stability of the proton. The scale is large enough that suppresses this operator. So when you move to dark matter, the assumptions that people make, they seem quite different. In particular, people seem quite comfortable with imposing global symmetries. And it all began, I think, with supersymmetry, where you impose a discrete symmetry, Z2 symmetry, which is our parity, under which the standard model particles are even, the SUSY particles are odd. And this guarantees that the lightest supersymmetric particle is stable, and it will be the dark matter candidate. So this, however, from the point of view of the standard, I think it has never looked very good. And so I think it's a natural question to ask whether the dark matter can be accidentally stable as the proton. And so if you try to answer this question, you are almost unavoidably led to introducing dark gauge forces. And what I will talk about today is the possibility that the dark matter is an accidentally stable dark hadron. So specifically, I will work with where you extend the standard model with an unabelian gauge theory with fermions. And the interactions with the standard model, they are determined by the quantum numbers of these fermions. So in particular, if these fermions have standard model charges, they will interact with the standard model with gauge interactions and possibly also through Yukawa interactions. Now, this framework is nice from the point of view of dark matter because, as I mentioned, it gives you automatically stable particles because of accidental symmetries. So in particular, as in the standard model, you have a dark baryon number, which is an accidental symmetry, and this guarantees the stability of the lightest baryon in the theory. You can have other symmetries, such as accidental symmetries, such as species number, and this guarantees the stability of some mesons. And moreover, if you have a decoupled sector, which we will consider in a moment, the lightest particle of the sector is also accidentally stable because the edge momentum tensor of the dark sector is accidentally conserved. So now there is two possibilities. So if the dark sector has standard model charges, this leads to exciting scenarios from the point of view of experiments. So first of all, this type of framework has a nice feature that it doesn't ruin the success of the standard model. In particular, flavor is almost as good, so it's almost as good as the standard model. You have more small correction to precision observables because this sector does not break electric symmetry. And so the main constraints that come from direct search is at LHC, which, however, are not terribly strong for this type of sectors. Of course, here you are not trying to address the hierarchy problem at this level. Okay? So while this is does not ruin the standard model, and there is not many theories that do that, the phenomenology is quite interesting. So if you are lucky, this can be testable at LHC. It has also implications for Higgs physics because the Higgs can mix with some resonance of the dark sector. And what I will focus today is, well, what I will focus in this talk is the fact that this framework has an automatic accidental dark matter candidate. So let me spend just a moment discussing the case where this sector has standard charges. So in this case, the most promising dark matter candidate is a baryon of the dark sector, and this can be done in many different ways, starting from SU engaged theory, with different dark matter candidates. In one case,
di Michele.
Yes.
Dark matter.
Ma non dire, cancella subito quello che stai ascoltando, che mi vergogno di te.
Baryonic dark matter.
Volevo solo sapere, tu che tipo un argomento tipo il monopolo di Dirac, viene considerato
maybe you can mute.
Careful with your
ci parlo un momento.
Can you?
Vabbè, cioè,
I think it's possible to mute it.
Yeah, can you guys mute it?
Tu hai seguito topologia differenziale.
Sì.
Allora,
Cioè,
speri che lo studente ha già seguito
perché
così,
quindi è in grado di...
Sì.
Aldo Lorenzo, something. Can you please mute yourself?
A te devo mandare una mail, a te ti posso mandare anche...
Yes, yes. Oh, thank you.
So you have many declinations of this idea. Okay, so for example, if the quarks are light and the dark matter abundance is obtained through thermodecoupling, so this the abundance is controlled by the annihilation cross section of baryons, which is as large as allowed by perturbativity bound, and this will give you a dark matter mass in the 100 TeV range. You can also consider scenarios where the quarks are heavy. This gives the different results. In particular, the dark matter is a weakly coupled bound state with complicated cosmology. You can also consider the case of light composite fermions, which give a very different phenomenology. So just to give you an idea, one very simple scenario is the so-called composite Wino scenario. Which is just an SU3 gauge theory with a fermion which is a triplet of SU2 of the standard model, and the lightest state is the baryon made of three triplets, and the lightest state inside this is also a triplet. So what you get at the end is just a triplet of SU2, which is, however, is stable because of accidental symmetries. Predictions for experiments will be very different because the mass is very different. For example, in this case, if I take literally 100 TeV and no other variation to this model, I would end up below the neutrino floor. So this is great, very exciting, perhaps. But during pandemic, we felt that maybe it was, after all, wishful thinking that the dark sector was not so dark. So we decided to consider the nightmare scenario where the dark sector is truly neutral under the standard model and see what we can say about this possibility from a technical point of view. I think is completely fine. So we consider this possibility. So with the new sector which is neutral under the standard model and just talks to the standard model through gravity, and we also allow wherever is relevant, Planck suppress higher dimensional operators. So since this sector is completely dark, one has to mention how you produce this sector, and there is really many ways to produce the dark sector. One unavoidable way is through freezing using gravitational interactions, so producing the dark matter directly from standard model thermal bath. And so in this case, the abundance is controlled by the annihilation of dark matter into the standard model thermal bath. And so in full generality, this can be related to the two-point function of the energy momentum tensor of this sector. Now, for gravitational production, the production is strong at the highest possible temperatures, where the sector is in fact relativistic. And so in this regime, the two-point function of the energy momentum tensor is fixed up to a coefficient. This coefficient is what in conformal field theory is called central charge. And so you get the extremely simple formula for the energy density of the dark sector at production. You can so you can generalize this to contact interactions, for example, and if you have low-dimensional operators, this can give a stronger contribution to the production of dark sector than gravity itself. Another mechanism that people discuss is production through fluctuation. That is, particles are produced by quantum fluctuation in a time-dependent background. Now, for these two, this mechanism requires that you have some breaking of Weil invariance, which can be stated as the fact that the trace of the energy momentum tensor should be different from zero. And in our context, what that this is negligible for our gauge theory with fermions in the region where we reproduce dark matter. You can even have simpler mechanisms to populate the dark sector. For example, the inflaton could have a width in the dark sector, and this would could easily dominate the gravitational production. And finally, you could have a bridge between the two sectors at a remarkable level, and this will force the temperature of the dark sector to be equal to the one of the visible sector at the early stage. This last scenario actually will be mostly excluded at the end of the day. Yeah. No. This well, it's very so. For example, in this framework, you just start the fermion, which has charges and the standard model. This would provide a bridge between the two sectors that will equilibrate the two sectors at high temperatures. Okay, so and of course there is many other mechanisms that you might imagine. So in this context, let me start from possibly the simplest theory that of dark matter in the dark sector, which is just a pure glue gauge theory. And to be concrete, we might consider an SU3 gauge theory for which there is a lot of volatile results. For example, the ratio of the mass of the lightest blue ball to lambda, which is here the critical temperature of the dark sector, or the latent heat divided by lambda to the fourth. Now, because of accidental symmetries, the lightest blue ball is automatically stable, and it will decay unavoidably to graviton with this rate, which is parametrically the same as a dimension 6 operator. Moreover, in this theory, the leading operator beyond the remarkable level is also dimension 6. So it makes sense just to focus on decays to gravitons, which is guaranteed, while any higher dimension operator is anyway model dependent. Now, this model has been considered before, and it is known that in order to avoid constraints from fraction formation, because otherwise the dark matter will be too light, and also self-interactions, because these blue balls are strongly interacting, you need to have that the temperature of the dark set initially must be less than the visible temperature T. Now, from this point of view, gravitational production looks very nice because it's minimal and because it gives you automatically a very cold dark sector. So you can compute precisely the abundance of the gluons in the confined regime just with the formula that I wrote before, in terms of this central charge, which is, to be precise, is 16 times 8. 16 is the central charge of one gauge, massless gauge field. So this is the initial abundance of gluons. And one important thing that that I didn't say before, let me just step back for a moment. So when you produce a particle through freezing, the typical density, the typical energy that of the particles is of the order of the temperature of the standard model thermal bath, okay, which is T here. So this is the energy of each gluon, but because gravity is so weak, the number of gluons that you produce is very small. So there is this suppression in the density, which is T reheating divided by m Planck cube. So essentially, you have a gas of very relativistic particles, but extremely dilute. So extremely out of equilibrium. This is this sector. So what will happen next is that interactions will try to go towards thermal equilibrium of the dark sector. And the way it is achieved is by lowering the typical energy of the gluons. So through processes that increase the number of gluons. For example, for processes where from 2 gluons you go to 3 gluons. Okay? Of course, you cannot just stop to this process. However, parametrically, this cross section for number changing gluons in the regime will scale like 1 over T square. And the rate will just be the density, which is the yield Planck's, which goes like TR over m Planck cube times T cube. Okay, so this is the rate of the number changing interactions. And so thermalization, unless you hit confinement before, will take place unavoidably when this rate becomes of the same order allowable. So this takes place at a visible temperature, T star, which is given by this formula, which is just obtained by solving gamma of the order of h. Now, if thermalization takes place in the relativistic regime, then you can just get the dark sector temperature after thermalization by energy conservation, and it is given by this formula. Okay, so the ratio of temperature Td over T, it goes like reheating temperature divided by m Planck to the 3/4. Okay, so at points if this system has indeed thermalized, it will continue its own thermal history independently of the standard model, and you can compute the abundance of glue balls, just for example, estimate in terms from energy conservation in terms of the energy of the thermal bath of gluons and the latent heat during the phase transition. So at the end, so all these things scale like inverse powers of m Planck, but you see that you find strange powers because of the thermalization. So this translates in an abundance of the dark loopholes, which is given by this formula, which means, for example, that for reheating temperature 10 to the 15 GeV, you have that the critical mass of the globules is of the order of 10 GeV. Now, the physics of this dark sector is in fact quite complicated, and after the phase transition where you form the globules, you may have exotic phases such as cannibalism. So this takes place if the number changing interactions 3 to 2 in the non-relativistic regime are faster than possible. And so this leads to some minor modification in the abundance, but to an important modification in the temperature of the dark sector. Okay? Important in general, but in this case, the sectors started so cold that they will be still cold at the end of the day. Now, since this plasma, which you produce through gravitational interactions, is very dilute, it's also possible that the interactions are not strong enough and the system will not thermalize. Okay? So this means that before, so I was discussing thermalization in the relativistic regime. Before you thermalize, you hit the confinement scale. Okay? So this takes place for mass of the glucose bigger than this value. And so it's a very non-standard situation. So the physics is complicated. I don't know for sure what is the result of the dynamics, but the way we argue is the following. So we estimated the temperature, the visible temperature where the phase transition takes place in terms of the density of the dark gluons. So when the density becomes of the order of lambda cube, it means that two gluons are separated by a distance 1 over lambda. And so this should be the place where confinement is taking place. At this point, this is not okay. Each gluon has an energy which is parametrically larger than the dynamical scale, and so what happens is that each gluon starts moving in the confinement vacuum, so a bit like energy gluons at LHC. Okay? So this will produce a showering of the gluon, producing many glue balls as allowed by conservation of energy. And this is relevant for dark matter because if you increase the number of gluons, you change the abundance of dark matter. Okay? So this is the summary plot for glue ball dark matter, the plane reheating temperature to confinement scale. And so in this lower region, you actually find that cannibalism. So in this lower region, you find that the phase transition takes place in equilibrium. Okay, and so you also have a phase of cannibalism. Here you have a different phase that maybe I will not discuss. And in this upper region, instead, we consider this possibility that the phase transition out of equilibrium increases the number of particles. So this is the reason why you have this funny shape here. Okay. So the bounds that you have in this theory are just 3, I think. So one is from the bullet cluster because you have intrinsically self-interactions of dark matter. Then for gravitational production, you are led to very large reheating temperature, and this is constrained by the absence of temporal modes so far. And so then there is also in the upper region this bound on the stability of the dark blue balls. So this is the story for dark blue balls. Any questions so far? Yeah.
Yeah. So for question, please, in the middle.
Sorry.
So first, in your previous slide, could you explain the last equation, and also in the slide the next slide, could you explain the 3 regions for the control lines?
3 regions.
Yes.
Okay.
Thank you.
So in this lower region, okay, you have that. So you have thermalization in the relativistic regime. Okay. So here, actually, you don't thermalize in the relativistic regime, okay? But as far as we can tell, it's very likely that you will thermalize in the relativistic regime. So at the level of the theory of glue balls. Okay. So 3-to-2 interactions, they are fast enough. Okay. So in that case, again, everything thermalizes. In this upper region, okay, because this, so you see, as you increase lambda, this sector it becomes so dilute, okay, that it never thermalizes. Okay, in that case, so we suggest that there is this enhancement from the production of gluons per each of glue balls from each gluon. Okay, so in practice, we never find and region where okay. So in the context of gravitational freezing, people, most papers that I know at least, did not consider interactions. You are also considering interactions now, I think. Okay, but I mean, there is a long literature, and interactions were not much considered. They are very relevant, so they change the abundance, and so the dynamics after production is also important. Okay, yeah.
In the white region, what are the observational consequences?
As far as I can tell, there is no other constraints from this.
No, but as far as discovering this scenario, as long as you are in the white region, you.
Well, I think that if you discover tensor modes, okay, this would boost a bit your confidence in in a scenario where you have such a large reheating temperature. Okay? So anyway, prediction here is that the reheating temperature should be very large. Okay? But of course, there is nothing that really will. There is no really smoking gun for that I can see. Okay? So unfortunately.
What about like gravitational waves from the phase transition that you were talking about?
Great. I have a slide at the end if I make it. Okay. So there can be a phase transition. So maybe I'll wait.
So what is the variable Mdg?
So this, of course, we don't know. It is we are phase. Okay, when you have this gluon high energetic, how many particles will shower? Okay, we can imagine that is like a LAC. Okay, but we don't know. So we just played, to see how things go. Okay, so don't take this too literally. Okay, but I think the question of this completely out of equilibrium phase transition is in principle interesting on its own. Okay.
Just a related question, very simple. We are to understand in the second regime at some point, it doesn't matter what the Mdg is, right? It's not that only if it's exactly 100, right? I mean, just
yes.
right.
So
like
the point is that as long as you
become
thermalize at some point, then the memory is completely erased. Okay, and essentially the abundance is fixed by energy conservation. Okay, so this was perhaps the simplest theory. And next, sorry.
Move on, just one quick second. So where is the bullet cluster constraint actually coming from?
Because
how do you know this?
Yeah, these group also have a self-interaction. It's strongly coupled objects. So you might imagine something strongly coupled. This has also been checked on the lattice, apparently.
Okay, that's what I was asking. Is it just an NDA estimate, or is there a lattice
So
calculation?
so the NDA estimate is not too far off from the lattice result. Okay. Yeah, it depends what precision you want. Okay, so here you could be precise actually about the bullet cluster constraint. Okay. So let's move to the next scenario that we consider afterwards. Okay, so which is just a theory which is like UCD. So we consider an SUN gauge theory with light fermions. So the spectrum will be similar to QCD with pions and baryons. And because this sector is completely secluded, you have, and because of that accidental baryon number conservation, you have the lightest baryon, the last dark pion are automatic dark matter candidates. Now, this scenario is quite different, in particular because the leading interactions with the star model is dimension 5. And so in particular, this dimension 5 operator with the Higgs portal, it will allow the lightest pion to decay. And the lifetime, it will depend strongly on the mass of this pion. So in particular, if the pion is heavier than twice the mass of the Higgs, this will be very short-lived. On the other hand, if it's lighter than this, then the lifetime can be compatible with the cosmological stability of dark matter. The fact that so this, by the way, is also the reason why ion dark matter is, in my opinion, not as attractive in the case where the sector has standard model charges. Okay, in that case, the pion should be range, okay, to reproduce the abundance, and this is incompatible with cosmological stability of this dark matter candidate. So this is the parameter space in this theory. So in this blue region, is this blue because I'm colorblind? I hope. Okay, so in this region, the scenario is excluded because the pions decay after BBN. They are not cosmologically stable. In this darker region, the pions decay have a lifetime longer than the lifetime of the universe, but maybe not long enough. So this will depend on the details of how this pion will decay. So so let's say that the lighter region is certainly excluded. This one requires a more careful study. For baryons, on the other hand, actually they can only decay with a dimension 7 or higher operators, so they are cosmologically stable even for very, very large masses. Now, this dimension 5 operator allows for a stronger production through freezing, as you may suspect. And so this the scaling is just the separation is just reheating temperature divided by M Planck compared to something which is in thermal equilibrium. And so this naturally leads to a warmer dark sector. In fact, in this part, we'll not just focus on gravitational production, but we'll allow the dark sector temperature to be a free parameter. Also, because of this, is much more difficult to get to have an auto equilibrium phase transition that I was discussing in the case of gluons. So you have these two dark matter candidates. So let's start with pions. So you have this thermal buffer with a dark sector temperature, and at some point when the temperature drops below the critical temperature, you have the phase transition. At this point, essentially all energy in the plasma is converted into energy of relativistic pions, and so this gives you a yield of pions, which is the standard one, but multiplied by C cube. So so you get a suppression which is the dark sector temperature divided by T cube. So from this, for pions also, for what concerns this discussion, the interactions are not very important. So you can directly get the abundance, and the abundance is obtained for light masses of the dark pions. Moreover, because of stability, so using this value of the mass, we require that this ratio is larger than 10 to minus 3. So this sector cannot be arbitrarily called and reproduce dark matter with pions. For baryons, the situation is completely different. So from the point of view of baryons, the are a thermal path. So the dark baryons, they are doing a thermal freeze out from pions. If we take the pions to be relativistic, then this is controlled by this almost standard Boltzmann equation. The only thing to notice here is that this Hubble, so the temperature, so this Boltzmann equation is in terms of the dark sector temperature, and the balance is controlled by the dark sector temperature, but Hubble is typically driven by the visible sector. Okay? So you can find simply the balance. So it scales like this. So in particular, if the dark sector is colder than the visible sector, you find that the balance is just suppressed by 1 power of C. Okay? So this gives you a dark matter, which is so a baryon dark matter, which will be of the order of 100 TeV divided by this root square of C. And I remind you that 100 TeV comes from the annihilation cross-section of baryons, which is strongly coupled. So unavoidably, the baryons will be very heavy in this realization. If the pions are not relativistic when the baryons decouple, is a bit more complicated, but the end result is almost the same. There is another effect that is also important in a large fraction of parameter space, and it is the fact that the pions they're long-lived, and if they decay prior to BBN, they can still dominate the energy density of the universe, giving rise to an early phase of matter domination. When this happens, you have that when the pions decay, you have entropy injection in the Standard Model buff, and this reduces the abundance of dark matter. Parametrically, with this formula here, where gamma is the decay rate of the pions, and y is the yield of the pions prior to decay. Okay. So, important fact. In fact, if you this also allow to consider the scenario where the dark sector is initially hotter than a standard model. So the final yield is given by this abundance multiplied by this dilution factor, and in the limit c which goes to infinity, this you find that this is a finite limit, and so this is the abundance of dark matter. Okay. So in this picture, actually, dark matter is reheating the standard model. Okay. So and this well is it will be interesting at the end of the talk for gravitational waves. Okay, so let's get to technology. Of course, yeah.
Can glue balls do the same job?
Well, I'm discussing global dark matter, so no.
So it isn't the here dark matter the baryons diluted by the pions in the slide, or?
Yes. So the glue balls are heavy. So in this scenario, as in QCD, you don't expect them to be stable. Okay?
Yeah, but could they be long-lived? Or
I think it's, the glue balls are very unlikely to be long-lived. Okay, so if in nuclear physics of this dark sector there is somebody that is somewhat stable, then it could also do have effects. Okay, but glue balls in QCD is already difficult to find them. I mean, their width is comparable to the mass. Okay.
Yeah, they're light baryons.
So the glue balls are relevant in the scenario where the quarks are heavy, okay, which we could also consider here. But in that case, here I would just do glue ball dark matter.
Yeah, okay.
Yeah.
Just to be sure, you assume there's a symmetry between baryons and anti-baryons, right?
So I'm not injecting any asymmetry.
Yeah,
yes.
good. Just
which is another possibility, but it definitely requires extra ingredients to this picture, because so at the level that I'm discussing, baryon number is really a symmetry. Okay, so
just make sure. Thanks.
Yeah. Okay, so let's get to the phenomenology. Of course, it's still tough because this is a dark sector, but actually phenomenology is more interesting because in particular in the pion dark matter scenario, the pions are light, and these they can have different kind of effects. So first of all, just Lagrange, and you can extract what is the cross section for elastic scattering. It scales like m pi squared divided f to the fourth, and this constrained by the bullet cluster. Then, because dark matter is warm, this has effects on structure formation, because it can lead to too much free streaming. This is an important constraint. You can also consider a scenario where the pions are exactly massless, and the dark matter is made by baryons. In this case, you have so the pions are dark radiation, and there the bounds of CMB MBBN on dark radiation that constrains this the ratio of the visible of the dark sector temperature to the visible temperature. So this is a summary plot. Okay, so this now I will explain. So this is the full parameter space of the theory, many orders of magnitude. In each point in this plot, dark matter abundance is reproduced. On the dashed vertical lines, it is reproduced by the pions, and on the horizontal continuous lines, it is reproduced by the dark baryons. So if you are optimistic, you could say that half of the parameter space is already tested in this theory. Okay? Of course, it's not completely satisfactory. Given the starting point of a completely dark sector is well, it's I think it's interesting. So here, as I mentioned, so here you have effects due to dilution, for example, and well, this region here, as I said, is typically excluded by decay of the pions. Yeah.
What is F? Is it the confining scale?
So F, I'm using a convention of the Carroll-Lagrangian. Okay. So for me, the mass of a baryon is a 10F. Okay. So we are taking values from QCD. Okay. F in QCD is 93 MeV. Okay.
Is it not a problem to have F smaller than BBN? Ah, no, it's not.
So this region here is not a physical region, okay? Because the pions would be heavier than the for example, 5F. Yeah.
You probably said it and I missed it. How come chi equals 1 crosses chi equals 10 to the minus 4?
Sorry?
Like if I look at the right top plot, it looks like chi equals 1 is crossing with chi 10 to the minus 4.
Well, this has to do with dilution, okay, which will change the abundance. Okay, so dilution, if the dark sector is cold, is not very important. It's more important if it is warm. Okay.
So these are different parameters, or
this it should be well.
No, external parameters.
So here, what I'm doing, so in the plane, so there is two parameters, really simplifying everything, okay, which is the mass of the pion, and F, which is equivalent to the mass of the baryon. Okay, in each point, we are reproducing the dark matter abundance. Okay, so here I'm reproducing dark matter abundance with pions. Okay, you see that you are led to very light dark matter in this region here. Okay. And here I'm reproducing dark matter with baryons. Okay, everything else is excluded. Here is excluded by the Boole cluster. Here is excluded by decay of pions. Here is excluded by free streaming, and this region here is really relevant to the baryon scenario with massless pions. So it's a bit busy plot because it's a summary of this entire theory. Okay.
Why do you have an upper bound on F coming from baryon decay? It seems. No?
Why do I have an upper bound on F? Well, this is the cosmological stability. Okay. So if F is too large, then? So if F is too large, then the baryons will not be stable. Okay. So the mass of the baryon is of the order 10F.
What's the connection with this dark matter candidate and the standard model baryon?
No, this has nothing to do with standard model baryon. Sorry.
Ah, so you're talking about
this all dark sector. This is dark baryon.
I see.
Yeah.
Okay.
So in this case, the pion is never so which is the dark matter candidate, and if it is so, like when you consider, for example, bounds on the lifetime, do you consider because like you say, for example, there CMB stage 4 blah blah, but you also have bounds from CMB on the lifetime of dark matter, right? Because like that will alter, for example, the angular diameter distance, and then you will see it in Saxon-Wolf effect, for example.
Okay.
Did you consider that?
No, no. We were just consider like a really order of magnitude estimate. Okay. So also because some things will depend on the details of this sector. I'm oversimplifying, okay? Because as I mean, QCD it looks a lot more complicated than this. Okay. But I think this captures the you know, the main features, at least. Yeah.
I have a question. So maybe I missed it, but why, for example, like electron volt scale,
Yeah.
the free streaming constraints seem to disappear at
They should not disappear. Okay, just we didn't consider pion dark matter probably in this region. Yeah. But yes, so we cannot consider pion dark matter and small c. Okay. So and large c. Okay. So that would be anyway excluded. Okay. So large. So even c equal to 1 is only allowed if the pions decay. Okay. Because otherwise they will give you too much energy. Okay. So they're either excluded by dark radiation or too much dark matter, okay, or free streaming.
How shall we know?
Well, if you are lucky on the boundary, okay. Then,
Boundaries. Okay.
yeah, I can. It will be difficult to shrink this region. Okay, unfortunately, it would be very difficult. It would be great if there is other probes. These the obvious ones. Well, they do probe some region of parameter space, but to go here in the middle, I think you need new ideas for sure. I don't know if it will be possible. Yeah.
It's much smaller than the interiors.
Yeah, the measure is not really linear, probably. But it diverges. Okay. So let me mention something that we are doing now, which is a bit a spin-off of
Sorry,
this.
could I ask one
Yeah,
quick?
please.
Sorry, just to follow up with Salvas's comment. So even if, let's say CMBS4 measures delta ineffective of 0.05, and let's say that in-body simulations and bullet cluster tell me that actually I want self-interactions like right up against the bullet, like very close to.
Well, okay.
Yeah, so let's say we have both of the measurements, I guess. And then the question is, then how do I know we have this very
Well,
dark
if I had to
band?
saturate the bullet cluster bound, okay, then I have to be somewhere here. Okay. Still, you know, there is some regions that it would be. I don't know how to test at this moment. Okay.
I see. Because I mean,
maybe Raghu has some ideas. Yeah.
Yeah. Oh.
In response to your question, if you are very close to the boundary, probably there could be halo ellipticity test. Because self-interactions, they give you different eccentricities for the halos. So that's just at the border. But
my generic question is, you know, I have 100 models of self-interacting stuff that a little bit affected. So I guess my question is more broad.
Yeah.
How do I tell one are, you know, completely dark matter with self-interactions and effective from the next model with, I mean, if you have additional interactions, of course, but I just don't know how to test. You know,
well, for example, if you, well, first of all, the bullet cluster is somewhat in tension with the cross section that you will need to solve short distance scales.
Yeah, that's right.
So from this point of view, for example, in these type of sectors, you can have a velocity dependence of the cross section.
In
so,
some sense it's preferred.
So,
right? That's why I say, you know,
but the question of distinguishing, of course, is extremely tough. Yeah. So, it's, yeah.
Yeah.
Okay, so let me mention some spin-off more in the direction we went, but a bit tangential to this current work, okay, but motivated by this work. So I mentioned free streaming. One interesting fact, however, is that dark matter here is interacting, And in this light dark matter parameter space, in fact, you find that in this red region here, okay, dark matter is remains self-coupled even in the non-relativistic regime. Okay, this is because of the self-interactions of the pions. So in this case, structure. So the evolution of the perturbation is different, and so in principle you have to do a more refined analysis. So we were motivated in particular by this paper to look into this. So let me phrase the result in terms of the benchmark model, which is a stereo neutrino with a temperature which reproduces the abundance of dark matter. So for just free streaming, the typical bound, the bound that people quote is of the order of 3.5 keV. In this case, so this corresponds at the level of the linear power spectrum to this blue line here, while cold dark matter will be this dashed line. So if you have interacting dark matter, the evolution of perturbation is technically different, okay? But at the end, the result is not vastly different. So this the curve that we find in the fluid approximation, and so from this it follows that, for example, the warm dark matter bound is somewhat relaxed. So, for example, warm dark matter will be will move from 3.5 keV to 3 keV. Okay, so and the same will happen also in our case. Of course, in the plot I showed before, you will not see the difference. So concluding, I just wanted to mention about gravity waves. So gravity waves, they seem a very good tool to study completely dark sectors. And in particular, if you have these confining gauge theories, they often go undergo a first order phase transition. This is known to happen in SUN if you have a pure glue or number of or light flavors in this window. Now, I'm not terribly optimistic about gravity waves in this sector. Because even if the phase transition is first order, there is argument that it might proceed in quasi-equilibrium, conserving entropy, and this would lead to a very small production of gravity waves. Okay. However, just for so I think it's worth to be optimistic about this issue, and what I will say, even if does not apply strictly to the simplest theory that I will consider here, it can be realized in other models which feature a dark sector phase transition. Now, I will assume then that the phase transition is explosive, leading to production of gravity waves. Now, if the dark sector is colder than the standard model, then independently of everything, the gravity wave signal will be very small. Okay, and the reason is simply that if you take this optimistic estimate of gravity waves, you see that it goes like so the ratio of the energy of the vacuum to the energy of radiation to the square power for alpha less than 1. And so if the dark sector is called the visible sector, this goes like C to the 8. Okay, so it's a huge suppression. Okay, so even if you have the strongest phase transition that you might imagine, beta over H over the 1, this will give you a gravity wave signal very small. Okay. However, there is a way out of this, which is, of course, if this alpha becomes much bigger than 1. Okay. Now, in order to become much bigger than 1, this can either be realized if the dark sector is simply warmer than the visible, hotter than the visible sector, or if you have a phase of supercooling. Okay? The second, so let me just consider the second possibility. So in this case, you will have a large production of gravity waves according to this formula. but you have to take into account that the energy in dark sector will have to come back to the standard model. Okay, and this will give you some dilution. So the only way to get a significant gravity wave signal in this framework is if you have a strong superpooling phase of the dark sector, and after the phase transition, whatever left, which in our case is pions, decay quite rather quickly to the standard model. So we played this game literally with our theory about playing too many games, and so in our parameter space, this corresponds to this limit C, which goes to infinity, okay, where the dark sector is becoming much warmer, much hotter than the standard model. So in this case, so the abundance is given by this line, and the gravity wave frequency is even smaller than nanohertz. Okay, so this relies on gravitational couplings. Of course, deviating from these gravitational couplings, this can move, and so there can be probably scenarios where you do produce a visible signal of gravity waves, and some of this I think was explored in a recent paper here. Okay, and so I'm coming to the conclusions. I hope I'm in time, more or less. Okay, so if you take seriously the idea that dark matter should be accidentally stable rather than imposing symmetry, then you are led very quickly to consider new gauge interactions, build a lot of models along these lines. If the sector is not completely dark, but it has standard model charges, and the future will be bright, probably. And also we will know eventually. But I think we must be ready that this will not be the case. Okay, so this was the motivation of this work during pandemic, and so there is a couple of very simple scenarios that come out of this. So the first one is the dark blue balls that are produced through gravitational freezing. And so here there is interesting dynamics that leads to thermalization and also questions about out of equilibrium phase transition, which are theoretically interesting. And from logical level, you can get dark matter quite light of the order of GeV. Testing the scenario looks very, very challenging, of course. So then we explored the possibility that of dark sector more QCD-like. So in this case, you have two dark matter candidates, the lightest pion and the lightest baryon, and they behave completely differently. The dark baryon is very heavy, while the pions they lead to warm dark matter. And in the second case, be interesting phenology for structure formation and effective self interactions. And this type of framework, well, it also has maybe interesting consequence for gravity waves, depending on how the phase transition develops. So maybe not necessarily in a QCD-like theory, but so this is another possibility that probably we want to explore in the future. So thank you.
Thank you very much, Michele. So there were already so many questions, but are there others or maybe comments? Please, also from the people online that maybe for which maybe was more difficult to enter discussion, like this, maybe your best occasion, but there is one here, please.
In your last plot, so in this green region, you said there was incompatibility between dark matter abundance and gravity wave observations.
Yes.
So why is this?
What is this?
So yes, incompatibility between dark matter abundance and supercooling.
So first of all, for this to work at all, okay, the only possibility that I see is that the dark sector is initially well, it's hotter than the standard model. Okay, so you have to go in this limited C, which goes to infinity. Okay, to maximize the gravity wave production. Then you want to avoid too much dilution, okay, from late decay of the pions, or if not pions, whatever light states are populated from the phase transition. Okay, and so this that of course should also decay before BBM. And so the interplay of these two will determine what is well the peak frequency, okay, and the abundance of gravity waves. By the way, here you find that the peak frequency is actually almost parallel to the abundance. This is completely accidental. In other theories, it could be different. Okay, it has to do with the scaling of abundance and dilution. Okay, that you have here. Okay? So if you look carefully, they're not quite parallel, and because it looks like miraculous, no?
Other questions or comments? From someone online, maybe? In case, just unmute yourself and ask. Yes.
The pions almost act like inflatons. It's like they dominate the energy density for a short time, and then they decay to ordinary matter.
But they're not inflaton.
No,
Okay.
they're not inflatons. No.
Yes.
But temporarily.
Yeah, temporarily they no. The problem is that you had to start because of this C to the 8 factor. You had to start from something which is hotter than the stomach. Then this energy density will have to go somewhere. Okay, and go to the lighter states that you have in the sector. To make a scenario, this has to come back to the stomach model. It comes, you know, the more you will get larger amplitude. Okay. So here, this was obtained not trying to, you know, to fit any experiment, just by putting like Planck suppressed decay width. Okay, I'm sure that changing that you get, you know, different, perhaps. So this is a bit below nanogram. Okay. Yes. So, well, I think that if we play parameters, we can get there. Okay.
So I just forget at what level of omega GW those experiments would be sensitive. It's very close to what you have there. I forget the exact number, but the point is that those frequencies, I'm repeating, those frequencies are so low that any time correlation is not humanly tractable.
Okay.
You need to do spatial correlations.
Okay.
And
yes, this is something that we are trying
yes.
to explore more. Okay.
Yes.
There must be other theories that, let's say that there is some, you see some peak spectrum and so on. There must be other theories that can produce this.
Yeah, I mean, here the only thing that enters is the latent heat of the phase transition bit of H. So,
right.
So
it would be very hard to nail.
Also, yes. Yeah, I'm not advocating that this a prediction of this model, also because I think that dark QCD, so gauge theories typically will not give you this type of explosive phase transition. Okay.
So if you have these dark baryons, and is it clear that they do or they don't form dark atoms without electrons, like dark nuclei? Like some.
Oh, thank you for the question. This is very no. In general, they will. Okay. It depends on their mass. Okay.
And
now, if they are incredibly heavy, so if they're very heavy, their density is so small, then typically the formation will be suppressed. Okay. However, in this type of theories, we have very often a phase of early matter domination, and there you could go structures and you could boost this production. So it is possible that you form maybe larger nuclei. Okay, so particularly for this question of nuclei, the phase of early matter domination can be very relevant. Okay,
and
so you
could you form I don't know. So could you form something like dark stars via some gravity? If it's a lighter state, you have some gravity that makes them want to come together like a star. I mean,
yeah.
then if you could
Okay, that's the other obvious question. Yeah. So this has been studied. Okay, so since you have this early matter phase domination, okay, you will actually start formation in the dark sector. Okay, at that point, and you can form structure. You can form dark halos. Unfortunately, most of the energy density is in the pions, and eventually these pions will decay. Okay? So according to recent papers, this will completely destroy these halos. So you might not be left with anything. But for the question of nuclei formation, maybe this I don't think this would be the case. So that could happen even for large masses. Okay. So yeah. So let's say that so we started this question for dark matter, for dark baryons with visible with some other charges, and we were finding that the production of nuclei like deuterium or similar, it could be relevant in the TeV range. Okay? In the 100 TeV range, this is way suppressed. Okay? Also because it goes like square of energy density. Yeah.
Well, I don't see any.
You have a question?
I see one.
Oh.
Yeah.
Here I see that the frequency of the peak of the gravity wave signal is in the nanohertz regime, but the corresponding confinement scale is in the PeV regime. So normally the peak frequency is set by the Hubble scale at the time of the phase transition.
But here there is this rescaling, this dilution that must be taken into account. Okay, so this will change everything. Okay, so here the limit where the energy after the phase transition is dominated by the pions. Okay, the total budget. Okay, and these pions, they are all decaying into the standard model, so they redshift, so they lower the frequency through this dilution. Okay,
I see. It's a big dilution.
Well, the dilution is crucial because yeah.
Because without dilution for PeV confinement scale, I would expect kilohertz for the frequency. So there is a
so let's see.
How is it possible? Because it seems there is 12 order of magnitude between the expected frequency and what is written here.
Well, quantitatively, I don't know. We didn't try. Okay, harder to fit anything. This is what we can. So the dilution is a very large factor.
Okay.
Maybe Andrea remembers. No.
It's like a dilution factor of 10 to the 12, maybe. The dilution factor seems to be around 10 to the 12 or larger.
That seems a lot, but we can.
Okay.
Yeah, okay. This paper, I think it plays a game along these lines in a completely different region parameters. Okay.
Okay. Any hands up? Any mics unmuted? If not, we thank Michele again and all of you for. And see you tomorrow at 4 p.m. for 2 talks this time on dark matter, 2 shorter talks.